this is the outline of this is actually things where you want to have high bit rates and very low latency, and you want to have that low latency even in those cases where the network may be loaded, which can happen also with 5G. Not necessarily that the 5G access is limited, but it could be other links on the path between the content and the end user, or between machines and the internet. This is sort of the outline of the whole program. And typical favorite application could be AR, VR, gaming, and also remote control of cars and drones and whatever you might want to control remotely. And so just to have an outline is that and 5G that is being rolled out and in various places on the world, and you have and you can get a very low latency and very high bit rates, especially in downlink and also for uplink traffic. And it can give a high capacity to enhancements like beamforming, and you can use several frequency bands, and also you can get very low delay. And if we want to do some kind of comparison, I feel what the problem I'm going to talk about is that you can see internet almost like roads. And here I have example of the northern hemisphere, and you can make a comparison between IP packets or whatever packets that you transmit on the internet. That also corresponds to cars and buses and bikes, and then flows. There could be traffic from one place to another, and you can imagine, for instance, that you want to go from Kuusamo, for instance, take one exotic place in Finland, and you want to go to Tromsø. And then you can easily see that you can take many different routes on that path. And what you don't know when you start to travel is that you don't know about the weather conditions and traffic conditions. Could be foggy, it could be icy roads, could be snow, and it could be heavy traffic along the long way. You don't know when you start your journey. And the problem is that when you start your journey and you want to sort of notify your relatives that don't come today, that the roads are horrible, then you actually, if you take the internet analogy, then you actually need to go all the way back to Kuusamo to tell them that the traffic is bad. That is roughly how internet traffic works. A bit trivial perhaps, but just get the analogy. And what we have today is that what you do measure internet congestion is that what you have in terms of being able to control the congestion is actually you measure packet loss and you measure delay. And if you take that road analogy again, you actually what you end up is that you have cars that crash and end up on the side of the roads, and sometimes you have traffic jams. And despite all this, actually the internet works pretty well today. You can watch your online video movies that are of favorite. But what the problem is that when you want to do applications that require low latency, then it can be problematic because you lose packets, and that can disturb your video experience, and you can get the delay spike that can make the video play out choppy. And another problem is here also that with the internet, you actually pick your traffic speed at the start of the journey. It's not like your normal traffic on the road, you sort of speed up and speed down. You need to pick your speed and how many cars you allow to go from one city to another already from the beginning. And typically also you react to those traffic jams or congestion when it's already too late and the queues start to build up on the network. What we want instead to get some control of it. And what we are looking at is that you want some kind of explicit signals that is sent back to the senders or to the cities where the traffic that the cars start from. And that is already on the way and maybe implemented in tomorrow's networks. And the outline of this is that you want to adapt the number of cars on the roads depending on the traffic conditions. It's pretty much like the road signs that are dynamic. And the outline is that you want to avoid traffic jams along the path from A to B, or whatever path that you take for your internet traffic. That is the goal that you want. And then we can discuss how should we do it. And the obvious thing, and you can take this one. And one example where you see this traffic congestion events that we have is we have a remote driving car that we have that are used with the 5G network up in Luleå here. And what you can see here is that you have on the control panel, you can see video quality and transmitted bit rates, and a little bit the statistics of round trip time and what the queue delays, actually, how much packets are queued up in the network. And in this particular case, we are actually on the border of the coverage of the network. So it's a bit problematic coverage. We only have one cell and that we need to reach, and that is some 400 meters away. So a bit challenging congestion conditions here. And if we look a bit closer here, we can see that we have delay spikes, those that are within red circles here. And that those degrade user experience. That what you see is actually when you drive that the video freezes temporarily, and it could be a bit unpleasant. And it would be really unpleasant. It would be a real one-ton car that you are driving. And what you want here is that we want explicit signals from the networks. Now the sort of the throughput start to degrade, or channel quality does start to degrade. Please reduce your transmission rate before bad things happen. And this you can realize with on the internet. You can realize with at least with two different ways. One is to use the speed signs that says this is the amount of megabit per second that you can sustain, that is sent back from the network back to the application. And then you can use the slow down signs. And the speed sign is roughly what like this. These are typical speed signs in along a Swedish country road, and you can have in the curve you might need to go down to 50 kilometers per hour. It could be a dynamic sign that is also changed dynamically depending on the weather and radio conditions and road conditions and how much traffic there is. Or it could be sort of stationary signals or signs here. And that is probably what you would see that the most obvious choice, because everybody knows what 90 kilometers per hour, that's good. And then you don't drive, preferably shouldn't drive faster than 90 kilometers per hour in order to get a speeding ticket or usual driver's license. But you can also use slow down signs. They all look a bit more strange perhaps, but what happens is that when you see a slow down sign, you slow down your speed a bit. But if you're still driving too fast, slow down signs will magically pop up along the roadside. Please slow down more. And there are some difference in this, and this is not really obvious. It doesn't change the specific speed. It just says slow down. And depending on the density of the slow down signs, and if more slow down signs pop up, then you slow down even more. And if you don't see any slow down signs, then you increase your speed again. And there are some difference here. And what would you like to use on the internet? One is using the speed sign, and it looks quite easy at first sight, but the difference against normal roads on country roads is that the internet speeds that we are dealing with, they vary from a couple of 100 kilobit per second up to gigabit, or in foreseeable future terabit per second. So that makes those speed signs difficult. And also the number of cars on the roads, or number of packets on the internet, they range from a few to several million packets per second. So we're much larger dynamic. And also that each flow, that means traffic from one city to another in this case, if you take the road analogy, is that they must be handled the speed sign with dedicated signaling, and that is typically something that you need to put the information in the IP header, so send some specific signal back to the sender. And that looks easy on the at first glance, but when then you sort of end up with problems. You need to authenticate yourself in order to not get false information or things like that. You need to have a trust relationship, and also that each bottleneck must signal its max speed. And as I said before, you have traffic can traverse edge links that they can have sometimes limited throughput, or it can traverse bottlenecks links that have a very large throughput, but they can be occupied by the hundreds of flows. So that makes it a problem. And in the end, you end up with a signaling problem that the solution doesn't scale well. It scales pretty well in small deployments where you have sort of university campus networks or experiment networks. But if you want to deploy this over the whole internet, then you get the scaling problem. And we take the slowdown sign. And it looks really odd if you would use a slowdown sign for a normal road, but you will probably not do that. But the signal is very easy to signal to the cars on the internet. In reality, you actually just use 2 bits in the IP header to signal this. And this signal is detected by the receivers and sent back to the sender. Over typical protocol feedback that you are using. Is it TCP or is it QUIC or RTP? And also, this technology scales, and you can apply it regardless if your road or your internet traffic carry just a few cars or several million cars. The same principle that applies. So in the end, it's more scalable, and there is more hope that it will be deployed and used by, implemented by vendors and network vendors, and deployed and used by end hosts. And just to show that this is not just something that is just a paper and pen product, and to have a slowdown signal in reality, which is being standardized in IETF. This is a standardization forum for internet of all sorts. And L4S stands for low latency, low loss, and scalable throughput. And low loss here means that you use these ECN bits to signal congestion. You don't drop packets, which means that you will have very low packet loss. And that would be mainly because you have link errors, for instance, over transport networks, which are often quite rare. And in this case, there's a simulation example with varying link throughput. Link throughput goes down from 40 megabit per second to 20 megabit per second in the middle of this simulation. And if you use congestion control based on packet loss and delay, which you see in this left-hand graph here, you see the transmit rate follows the link throughput degradation quite well. But what you also see is that the packets are delayed, which means that they are piled up in the bottleneck. And that is not an issue if you have traffic that is you don't care about the delay. But if you want to run your online video game or use your VR headset, that becomes problematic because we'll see that the video will play out in a choppy way, or the video will freeze, and can be a really exhausting experience in the end. And if you use this L4S technology instead, then you get a very early warning when the packets start to pile up, and you are able to reduce the transmission rate before bad things happen. And you can see in this case, you have almost over 100 millisecond extra queuing delay in the network. Whereas if you use L4S, you have to end up like 10 milliseconds more in this case. And as I said before, L4S is standardized in the IETF, and it will be soon an experimental standard that can be experimented with. And also can say that it's a complement to quality of service. It's nothing instead of quality of service. You can still use your slicing technology or a 5G cost framework to enhance the quality of or the priority of certain traffic. This is just a signal to indicate that the sender should reduce the sending rate in order to avoid getting bad performance for latency critical applications. And to make a conclusion about this, that we already said that 5G offers high speed and capacity at a low delay. But you can have congestion. It could be in the radio nodes, but it could be transport nodes, and it could be at any places. Those congestion hotspots are typically sort of bridged with or compensate with higher capacity over time. But higher capacity always drives demand for a higher capacity. So you always have a chicken race there where congestion can occur. And also that the congestion can degrade performance of applications that require low delay and high bit rate, and which is the case when you have novel applications that use augmented reality or virtual reality, or gaming applications also. And what we support here is that use an explicit speed control signal, which is called L4S, to help the application to keep the delay low. And that is the final